Okay, so after this very nice lecture about superstructure optimization, what I'm going to show is another parallel effort in trying to also formulate superstructure and based on superstructure, the optimization, but in a slightly different way. I will not go into the mathematics of it because we are directly, after we formulate the problem, we just use the solvers available in GAMS to solve the problem. So I will discuss more on how we set up the problem and then the solution options that we have. Okay. So again, as I talked about before, we are talking about the synthesis stage. And now I talked about the heuristic method of Douglas. I gave you the group contribution, enumeration, and test method. Now we will see about the superstructure optimization in a slightly different way than Professor Grossman's work, but many of the things are very similar. So superstructure of alternatives, as the question also was asked, what is the difference between flowsheet and superstructure? Flowsheet is just one solution, one feasible solution within the network of flowsheets in a superstructure. So again, what you see is in a simple way, how we represent a superstructure. In our case, we have raw materials on the left, and that can be more than one. We have products on the right, that can be more than one. And then in between, we have what you see as process 1, 2, 3. These are processing steps. That can be a reactor, that can be a mixer, that can be a separator, distillation or membrane or whatever. And then for each of those process 1, 2, 3, what you see as 3, 4, 5, these are different alternatives that this step can be done. So then you can see that even in this simple case, one needs to find out which is the best. If we want to ask the question, we want to use one raw material, we want to produce one product, and what is the path that is the flow sheet that will give us this product. So this is the superstructure of alternatives, our way of showing the superstructure. So each of those processes perform a task, and there are multiple ways to perform the task, which is the interval. And these can be based on technological developments that we know of, or we can put ourselves. So then you can see that the ones in green, 1, going to 4, going to 6, going to the top product is the optimal solution. And that's the flow sheet. So that's one flow sheet we get out of the optimization of the superstructure. Now, to solve this problem, we also need models. What is happening inside each of those intervals? So all the boxes under a process is an interval. So within an interval, we say that within the interval, there can be mixing, there can be reaction, there can be separation of waste, there can be product separation, there can be one, there can be all, or there can be nothing. If there is nothing, then it's a blank box just to bypass that process step, or there can be everything going on. So then it can be like a process within a process. So we have this, what we call a generic processing interval model. Now, for each of those operations within that interval, we need a mathematical model. So we need to derive those mathematical model. And then once we represent the superstructure from the library, we get all the models that is happening in each of the intervals. Then all the equations taken together will be the model that we want to solve. So in a more expanded way, you can see the mixing. We also have a nomenclature that what goes horizontally is the process stream, the chemicals that we are interested in. What comes vertically are the utilities and the waste. So that's the convention we keep. So from left to right, we are tracking the chemicals that we are interested in. From top to bottom, we are tracking the utilities and the waste that goes out of the system. So the model equations, just as Professor Grossman showed, simple stoichiometric mass balance equations for the reactor, for the mixer, for the divider, that is a stream divider, and that is also a splitter. So a divider does not change the compositions, a splitter changes the composition in the streams going out. So it is a separator in some way. So we have models for these. And then we do first the mass balance. And once the component flow rates for all the streams are satisfied, are calculated, then using that component flow rates and either pressure or temperature, we calculate the other variable and the state of that. And once we know the state, we can calculate the energy balance. So we do it in 2 steps. First the mass balance, then the energy balance. So that's a very simple model. And if we collect all the models together, then you can see the model equations for mixing, reaction, waste separation, product separation, transportation, that also has been added. The capex, the objective function, and what you see as highlighted in green, these are the variables that needs to be specified. That is the parameters. So there's a lot of work that needs to be done to get the models working together with the parameters. So in the objective function, we need all the prices. The capex, we need the sizing parameters to calculate the cost. For the transportation, we need a transportation cost factor. For the product separation, we need the separation factors. For the reaction, we need the stoichiometry and the conversion. So all of these need to be given. And then once these are given, then we are able to, for the superstructure that will be drawn into the process, and from the definition of what is coming in each of the boxes, we will know which equation to extract from the library. And then we will have the objective function. We will have all the process equations that are needed. And then we will also, we can also define out of the different possible combinations, if we want to allow all combinations, or we want to remove some combinations. So for example, if we want to go from raw materials to processing step 1, if we want to say only one direction is possible, we can put the constraint. If we say both directions are possible, we can also put that constraint. So like that, we put that, and then there are feasible paths, there are infeasible paths, and then there is objective function calculation, which is based on solution of the model equations. So the way then the software works is that you define the problem, give the raw material, give the product you want, give the locations. It's possible to have different processing step in different locations. Then step 1.2 is superstructure generation based on the information about how many processing steps are there for each processing step, how many alternatives are there. Once all these things are given, it generates a superstructure. Once all the parameters are given, it checks for the data consistency in terms of, based on the reaction data, can the reaction actually take place? Based on the separation data, can the separation actually take place? All of that. And then it extracts from the library the generic model, and it is also possible to, in some cases, modify the model if necessary. Then once everything is ready, then it actually creates the code for GAMS. So the user does not have to write any code. It creates the code for GAMS, and then the user can launch the GAMS run. After the GAMS run is finished, Hopefully it has converged. If it is converged, it extracts the results and puts them into the interface so the user can see the result. Okay, so that's how the stage one of the synthesis problem works. A little bit more on the framework. You can see at the top the superstructure of alternatives. So this program, which is called SuperO, it generates that superstructure you can see on the right. Based on the superstructure, it has the library of generic model equations. It extracts the model equations. Then for the model and the process described, it has a database with information about the prices, the costs, everything. It takes the data from the database. If they're available, if they're not, the user has to give them. Then once the data, model, and superstructure are done, then it generates the GAMS code and it can go to the solver. So a little bit more on the structure. The problem data is structured in terms of different items, which we will show later on. The consistency checks are done. A graphical representation is possible. The cost, capital cost, is linearized. The model can be edited, and then the optimal solution is obtained, and one then sees the network. So in this case, through this interface, which is called SuperO, and the database and the model library, the user does not have to actually write any code. They just have to fill out the information that SuperO needs in order to solve the problem. But we do not give the GAMS code, sorry, the GAMS solver with SuperO. We just give the SuperO, it will generate the GAMS code, but then the user needs to have the license for GAMS to solve it. And then I will show some of the problems that we have solved. And you can see that you can solve for chemical process flow sheets, biorefineries, CO2 utilization, water management, specialty chemicals, many more. And we are continuously increasing the number of applications. Some of the newer applications I cannot show you because they are confidential. So I will highlight one example, which is a conceptual example, but you can see that network benchmark problem, wastewater network, sugarcane molasses biorefinery, dimethyl carbonate from CO2, biodiesel, methanol, DMC, other things to obtain from CO2, bioethanol biorefinery. So there are a lot of them. And also it is possible, if you see the circles and the connections below with A, B, C, D, that it is possible to do now in different ways to make the connections. And so by taking into account the transportation and saying that one part of the process is in one location, another is in another location. So the conceptual study is just to show that we can handle any chemical process and integrate it with others. So we want to produce a product C, and we have raw materials A and B with some fixed composition and with inerts. And there are two reactions. And what we want to do is also that the process is going to use water, and the water then is not clean. So then it has to go into a wastewater treatment facility, and we will synthesize that also, and then we will combine the two so that the clean water can be recycled and the amount of fresh water can be reduced. So you define the problem, definition of the scope, the constraints, the optimality condition, performance indicators. Those are things that are available, and the user can take them and put them into the objective function. I don't know why I'm getting the Zoom is asking me to admit people. Okay. So then we define the network, but here is where a lot of work is needed, the data collection. So the more data that we can collect, the bigger can be the superstructure. The less we will collect, the less will be, smaller will be the superstructure. So how much information do we need about doing a processing step? So for example, the reaction, if we have 5 different catalysts to perform the reaction, we have 5 different reactors. For the wastewater, if we know different ways to remove the metals, different way to remove the biodegradable mass, then we have different options in the wastewater treatment network. So we need to collect all those information, put them into the form that SuperO wants. If it is separation, the separation factor. If it is waste, the separation of the waste factor. If it is reaction, stoichiometry, and conversion, and so on. So that's the superstructure that we created then for the process network. So you can see that in reaction, we put 4 different reactors. For the separation, 1 is only 1, absorption is only 1, but afterwards, in step 9, we have 3 different ways to separate. This is just a conceptual example. So we did that based on the data that we could generate, and actually more like a real chemicals, real reaction, but the process did not exist. So then we have this flow sheet, but we don't draw the flow sheet. Actually, SuperO draws that flow sheet. And then we have the water network. Looking at the publications of wastewater treatment, we could identify different techniques for different separation parts, and then we created the network. And then the 2 networks need to be joined together. So you see the red and the blue, and then in between there is 1, and this is the converter. That means it takes all the wastewater from the process, feeds it to the wastewater treatment, and after solution, the clean water goes back to the process. And then we solve it for cost, raw material, utility, waste, and we can actually generate different kinds of objective function and so on. So in this problem, there were 155,000 continuous variables, 35 binary variables. Total number of equations was around 160. And then this is the optimal solution that you can get, or we got. And once you, the good thing about this also is that once the solution is obtained and it is working, one can change different problem formulations, different criteria, different constraints, and generate all kinds of other solutions one would like to get. I will not go through them, but it is possible to generate different case studies. And very briefly, I will show the overall superstructure with respect to conversion of biomass to different products. First is the sugarcane, then is 6 different biomass giving ethanol, and also some other products. Then the palm oil giving diesel and glycerol, and then microalgae giving diesel, glycerol, and some other products. So all of these can be solved as different subsections of the superstructure, or all of it together. I will just highlight you the superstructure and solution for the 6 different biomass giving ethanol. So the 6 different biomass can come from different countries. So we also put the countries. We also put the ethanol that will be sold in different countries. And then the idea was which country should use which raw material to make ethanol and sell to which country, and all the processing steps together. And it turned out that if we don't take into account transportation cost and other things, then cassava rhizome is the best raw material to make and the cheapest to make at location in Thailand. But if we take into account how much cassava rhizome is there available and what is the demand for ethanol and all of that, and then the need to transport the produced ethanol because of lower demand to another country, then the solution becomes different. I'm not showing you those solutions. In the references, you can see those solutions, but transportation can be taken into account. If all those things are not taken into account, it looks like cassava rhizome is a good way to make ethanol in Thailand at the cheapest price. And then you get the flow sheet. So as I said, the process synthesis gives the flow, gives the mass balance for it, and we can put the energy balance. If we also put the temperature pressure information, then it will be converted to an actual process flow sheet with the corresponding design. So we can do the design analysis, which we will talk tomorrow. So these are some of the other statistics with respect to the solver. I will skip this now. And then the final one is also we created a similar kind of superstructure for taking CO2, captured CO2. We are not putting the captured CO2 in here, but we can also add that. So we have the CO2 that is captured, and the condition is that CO2 must be a reactant and must not be a product. What are the different products we can make? So you can see here that we are making dimethyl ether and one other ethylene glycol. That seems to be the best, depending on the problem formulation we get. And this is a fairly large problem. So in summary, what I showed, not just myself now, but also previously, and also Professor Grossman, in stage 1, we showed how the synthesis problem can be formulated and solved. There are different ways to solve it. The means ends analysis, which I did not explain, but Professor Grossman did. The Douglas method that I explained how it can be used. And then the group contribution based enumeration, and that is one way to generate all the data and get the flow sheet very, very fast. And then the superstructure based optimization that will be solving the model equations. In our case, the models are simple mass balance. So those, unless there is a recycle back, the model equations are linear. And then we solve that mass balance, and then we add the temperature and pressure data so we can do the energy balance, and we can then go forward with it. So with that, I will end, and if there are questions, I will take the questions. And then after this, there will be a short presentation of the problem solution using the HD example by one of the Thai team, and which is Mr. Jakrapath, and then our software developer, Ms. Konkanak. She will show the actual demonstration of Pro-CAFD from step 1 all the way to step 5. We are not doing the simulation today. We are only generating the flow sheets. So that will be shown by Ms. Konkanak. So I will stop here. And if there are any questions, I can take some of them, or we go to the demonstration part. Are there any questions? Okay, then Jakrapad needs to start first.